turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists.
Hello and welcome to The Naked Scientists, the show where we bring you the latest breakthroughs in science, technology and medicine. With me, James Titko.
And with me, Chris Smith. Coming up, a landmark achievement. Nuclear fusion experiments produce a net energy output. So what does that really mean in practical terms? Also, glasses that soak up infrared to auto-demist. Sounds like a saving solution in this weather. And how magnets are helping to solve a pollution problem on the London Underground.
The Naked Scientists podcast is powered by ukfast.co.uk.
Described as a landmark achievement known as ignition or energy gain, earlier this week researchers at the US National Ignition Facility in California said fusion experiments there had released more energy than was pumped in by the high-powered laser they were using to kickstart their experiments. So why, if it is this an exciting outcome? Well, with us to explain, a nuclear physicist, Brian Appleby, he's at Imperial College, and Richard Dinan, who's the author of the book The Fusion Age, and he's also the CEO of Pulsar Fusion, which is a company developing fusion reactors. Brian, to you first, what's the buzz about fusion, and why do we think that this is the future?
Fusion has the potential to be a revolutionary energy source because essentially it's a form of nuclear energy, but unlike nuclear fission, which is what our current power plants are based on, fusion energy would produce very little radioactive waste. It would not be using fossil fuels, therefore would contribute very little to, say, greenhouse gas emissions. And finally, the fuel that we use for fusion is readily available. We can extract a lot of the fuel from seawater, and then we can breed the other fuel that we need for fusion in the reactors themselves. So it has the capability of being really revolutionary in terms of being an energy source. It's just tremendously difficult to do. And last week's experiment was essentially a landmark milestone where we've ticked one box on, some of the many challenges that we need to have a commercial fusion power source.
Clearly we know it works because that's how the sun works, and the sun has been there for billions of years, and we think it's going to be there for a few billion more. So what are the challenges then that we need to overcome to realise what the sun is doing down here on Earth?
Yes, so that's true. So we know it works, but what we've been striving to do for about 50 years is to do it in a controlled manner in a laboratory, whereby we can get out a precise amount of energy and we can essentially control all the stages of the experiment. So what we did last week, or what was done in Livermore in California, was there was more energy came out of the fusion fuel than was used to heat it up in the first place. However, that energy is coming out in the form of high energy neutrons. So what we have to do is we first of all have to scale up that experiment such that we can produce an actually useful amount of energy. And then secondly, we have to find ways of taking the energy from high energy neutrons and, generating electricity, which is a useful form of energy.
Richard, I suppose we've entered into this era now where we actually regard this not as something that's pie in the sky. People don't hear that you're running a company building fusion reactors and roll their eyes, I presume.
A few weeks ago, I was at a conference in Switzerland and I mentioned nuclear fusion as a possible technology, and one person in the audience actually laughed. They were saying, as if if that will ever happen. So the skepticism around fusion technology has been very real. So for everybody in the industry, this is really, really vindicating, and it's I think a lot of people are revising their paradigms now.
What sort of timescale are businesses like yours working towards? So when you're asking for investment, when you're getting people to come and put money into a venture, what is the timescale on the business plan?
Well, look, as we just said, fusion is what the sun is doing, but we don't have a sun. As people have mentioned, this is an amazing achievement, but there's still quite a lot to do. So with investment horizons, you're not talking about 3 to 5 year horizons until you get profit. This is for people who are making conscientious investments that they want their children to enjoy, and it's not something that a lot of venture capitalists, it doesn't fit their model still.
So Brian, when we actually are trying to surmount these challenges, what we're hearing about from California, they're using a laser to kickstart a reaction and measuring how much energy comes out. That presumably is one approach, because we've got other people doing similar experiments in the UK at JET in Oxfordshire. We've got this reactor that's an international collaboration, ITER, which is being built in France. And I think they're up to 23 or 24 billion they've spent on that so far, haven't they? But are all of these things working in a similar sort of direction, or are they all solving problems in different ways, and this is all incremental knowledge? How does this actually all add up?
In a very basic level, they're all trying to tackle the same problem, which is that in order to have a successful fusion experiment, you need to make the plasma, which is the fusion fuel, extremely hot. It needs to be hotter than the center of the sun, such that the fusion reactions can actually occur. And then secondly, you must somehow contain that plasma for a sufficiently long time, such that you get enough reactions to produce a useful amount of energy. So then there is a whole spectrum in different ways in which you can approach this heating plus confinement or containment problem. On the one end in Livermore, they're using lasers where essentially they don't really do any actual containment. They essentially slam the plasma together, they compress it, make it 10,000 times more dense than water, and that whole experiment is over in less than a billionth of a second. On the other scale, you've got something like JET, whereby you're essentially taking something plasma that's really low density and using magnetic fields to confine it and to do the containment. And then between these two ends of the spectrum, there are a lot of different approaches. Several of the startup companies are looking at different ways in which, you can do some sort of mixture of these sort of confinement and heating approaches. I think it's a rising tide that lifts all boats in that, when one experiment is successful, we learn about how the plasma behaves, which can be relevant to other experiments.
Richard, one of the missions of your company is going to be propulsion systems for space. How does fusion fit into that?
Well, I mean, look, as you just said, there are several ways of doing this. And what they've just done at NIF, which is called inertial confinement with these big lasers, a lot of scientists, have been very much focused on how we can do fusion rather than how we should do fusion. Because we've got to contain that. We've got to be able to use that and harness those neutrons for power. And I agree that sort of electromagnetic confinement, like what you were talking about at JET or at ITER, are very, very suited for power station fusion. But there's another promise that fusion gives us. It's not just the ability to power our planet indefinitely. It's the ability to leave our solar system. Because the same reaction that we just saw happen in America would give us exhaust speeds 1,000 times faster, if you like, than conventional space thrusters, which means Mars in 2 weeks. It's an incredible potential if it can be harnessed for propulsion. So it's harnessing that same power for more than one application.
You certainly make it very exciting, even if we're not quite there yet. It sounds like we're going to get there a lot faster, especially if we have one of your engines behind the project. Richard Diner, thank you very much, and also Brian Appleby from Imperial College. Great to have you both on the programme and bringing us up to speed with what's happened this week. James.
Well, from something that could help us in the medium to long term to something that could help us now. In fact, the last week would have been great. The current cold snap will mean many glasses wearers will be facing a familiar problem, fogging. Especially common in the era of masks, it's when damp air, like breath for instance, encounters the cold surface of your lenses. The water condenses into millions of tiny droplets that scatter the light coming through and obscure your view. Now, one way to deal with the problem, other than giving your glasses a wipe down, has been to add a water-attracting coating to lenses, which pulls the water droplets into a continuous thin film, preventing the scattering problem. But these coatings aren't very robust and often need frequent reapplication.
Well, now, Tom Schutzius, who is at the UTH Zurich University, has come up with a new way to solve this problem, potentially. He's got a coating which is made from tiny particles of gold. They're called gold nanoparticles, which are so small that they are actually transparent to visible light, but the right size to absorb bigger waves called infrared, otherwise known as heat. So it's invisible light that's hot, and that warms up the surface of the lens, and it can prevent condensation forming in the first place.
Fog is only really annoying because you want to see. So light is already present. So could you, for example, take advantage of, some ambient sunlight, maybe light in a room, what we first looked at was then what is really available to us. So if we stick with sunlight, there's quite a lot of light that of course comes to us in what's called the visible spectrum. And that actually accounts for about 50% of the energy. But there's actually another 50%, which is what we would feel is heat in the infrared wavelengths. And so that's what we played with. We focused then on trying to develop a coating which could absorb in this infrared regime while then being transparent in the visible.
That makes sense. For this layer to be any use on glasses, the coating, of course, has got to be transparent. So what did you arrive at? How did you overcome this problem?
The one that we ultimately settled on was using what's called a plasmonic effect. It's an effect where you have a metal particle. So metals are useful because they're electrically conductive. They got a lot of these free electrons that are available. If you basically take light, which has an electric field to it, and you impinge that on such a particle, you can cause these electrons to oscillate and move, and they can absorb some of that energy. There's different metals that are good for this, and one really nice one is gold. So gold has a good property that when it's a small particle and you hit it with visible light, this electron cloud that's around the particle can oscillate at resonance. So it becomes a very, very strong absorber at, let's say, a specific light wavelength there. And that's great. We settled on that and we said, okay, how could we tune that? So if you change the size, you can start to get to different wavelengths where it becomes a strong absorber. And then if you go with maybe 2 particles or 3 and you start to pack them close together, you can get not just one wavelength where you absorb, but a more broadband one. And so we tuned that packing and that structure in a way where it was transparent in the visible, but then for us, it was then more absorbing in the infrared. So we had this kind of nice balance of properties there.
I've got you, harnessing the power of the sun. How do you, because I don't think of gold as a transparent material.
You have to think for a second about the bulk gold. So when it's a bulk material there, like a film, it can look like a mirror, just like silver. But then when you start to break it up and you make it much, much smaller, so no longer a continuous film, but let's say tiny particles, it no longer possesses that bulk reflective behavior. And also just to give you a context, these little structures and particles that we use are much, much smaller than, let's say, the wavelength of light that they interact with. So it's sort of a nanoscale property that, that emerges there.
I think this kind of has answered my next question, but people will hear that this new coating contains gold, and that might make them wary that perhaps when they next go to the opticians, this anti-fog coating is going to be an expensive add-on to their new pair of glasses. Is that going to be the case, or are we dealing with such small amounts of gold?
It's sort of funny, right? Like, I don't know, I just bought some glasses recently, and they already do, of course, many layers there. And I don't even remember, but each sort of layer I had the impression was adding on quite a bit of cost to what I had. But the point is that because it's such a minute amount of material, I mean, it's extremely, extremely thin layers that we deal with. The cost in terms of the material is actually not a significant aspect to it. Although I'm not going to tell you if you had it on there, you can still tell your friends and family, of course, that you got gold on it and you're a bit fancier with it, but it won't be adding a significant cost.
And could this ultra thin layer with gold as a component be used for other purposes, or is it limited to the use of on glasses?
No, of course it can be used for other things. I think here we talk about it because it is very annoying, right, with the visibility and also safety issues as well for us. But you can also think about things like sensors. A lot of things nowadays, especially think about cars and all of that, rely on sensors, and they see a lot of times similarly like we do. So having fog there also can become a big issue. And so having such coatings can also bring benefits, not just for us and this rather annoying problem, but also to, I would say, these other more significant safety issues and sensing and so on and so forth.
Who would have thought gold could have such a functional purpose? That was Tom Schutzius with a new coating to stop lens surfaces from fogging up, and that paper was in Nature Nanotechnology.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, Perfect music for audio and video productions.
You're listening to The Naked Scientists with Chris Smith and with James Titko. Still to come, how magnets are helping to sort out a pollution problem on the London Underground. But first, 35% of our food comes directly from plants that need pollinating. So it really is in our best interest to understand the relationships between plants and their pollinators. And a new study has made a fascinating discovery, which is that some flowering plants can alter the chemistry of their petals to change the shapes of their cuticles. That's the plant outer skin. And this produces crinkled formations that are called striations on the flower surface. The result is a more jagged texture that also has the effect of altering the colour of the flower and making it more blue. But why do this? Speaking to Will Tingle from Cambridge's Sainsbury Laboratory, Edwidge Maru.
We were really surprised to find that all sorts of plants keep creating this striation. And what was interesting is that the striation, they are not perfect. So what do I mean by that is they don't have exactly the same thickness. They have a bit of variation in how spread they are on the cell. And this is what we call disorder. And different flowering plants have different amount of disorder, but this disorder always create the same color, always shift the effect toward the blue UV end of the spectrum. And that was for us the first cue that this wasn't by chance. Because in theory, you could create disorder that create all sorts of different colors. So why is it that it was always shift toward the blue? And one thing we know about is that actually blue and UV are color that pollinator can see really well. We can't see in the UV, but lots of insects can. So our idea was maybe this is a way plants use to create blue. And this was particularly interesting because it's quite difficult to make blue by other means. Using pigment to make blue is really tricky. People have been trying to create blue roses for a long time and it never works. It's never blue, it's like dark purple. And one idea we've got is it's also quite expensive and complicated to produce this pigment, whereas the cuticle is there no matter what. So creating the striation is quite simple. And it's a nice way to appear blue when you shouldn't, because you don't have the right pigment for it. So this was just an idea. And then we did all sorts of bee experiments to see if that real can be see it. And the long story is they can see it. And actually, if you create this striation, if you create this blue effect, it makes the flowers stand out more. So instead of spending a lot of time to look for flowers, the bee can see them much more efficiently. So our idea is that by creating this kind of structural color, this allow flower to really stand out from the crowd, and it gives them an advantage.
Was this striation the same in a plant that lived here as opposed to perhaps the same species of plant that lived in the tropics?
We use a collection of the garden, so lots of these species are not native to the UK, some of them are weed and they spread everywhere, some of them are much more local. So in theory, this kind of phenomenon can have emerged everywhere. What we realize is not so much a characteristic from where the plant lives, it's more a characteristic of the flower. So you can have flowers with complex shapes, some are really close, some are open. What we realize is all the flowers on which we detected this striation, they are kind of simple shape, a bit like a cup, and meaning that they are directly exposed to light. Because if you develop striation inside a flower that's closed, it makes little sense. You can't interact with the light. So it's more characteristic that these flowers have. The other characteristic is many of them, they don't remain open for very long, meaning that they have one shot at attracting pollinators. So maybe that's an extra selective pressure to be really shiny and really attractive.
How does then that play into our ability to conserve insects? Because a third of our food is created by pollinating. So hopefully that means that we could perhaps use this information to better conserve them.
Yeah, absolutely. So in theory, one of the motivation we've got to understand how plants fabricate this structure is once you understand how they are made, it gives you the ability to maybe engineer them, make them better, or transfer them to plants that cannot create this structure. So we haven't generated striation in plants that can't striate yet and study the effect, but in theory, it's something we could do. And more importantly, without even modifying plant, this can give us some idea of, if you want to enhance pollination, what kind of species would be good to introduce to a new medium, what kind of species are likely to stand out. And species called iridescent species, the species that can do this trick of light, might be a good way of making flower more salient.
And how do you think this can help us conserve these plants?
In terms of conservation, it's difficult because we are a long way from understanding how the pollinator interact with the plant in the natural habitat. All the experiments we've done with pollinator are in control condition, which is really helpful for us because we can be sure that what we observe is really due to the specific trait, so presence of striation, ability to create the color. What we need to do next is to go in the field and really observe what is happening. Especially we have some region where we have very similar species, but some with striation, some without. And there is at least one case when the species without striation seems to be declining. So it's easy for us to say, oh, it's declining because it's losing the striation, but we don't really know. So that's one thing we need to understand better.
Amazing that, isn't it? Edwidge Moreau there from the Botanic Gardens and the Sainsbury Laboratory in Cambridge. She just published that work in Current Biology. Now, last week here on The Naked Scientists, we looked at some examples of how magnets are making their mark in modern science. And a bit like London buses, another story about how magnets are making their mark has come straight along afterwards. Or maybe we should revise that and say not London buses but underground trains, because researchers at the University of Cambridge have been using magnetic techniques to find that the London Underground is polluted with tiny magnetic particles, including ones that are so small they can end up in the human bloodstream. You're never going to want to travel by tube again after this, are you? The results, which are published this week in the journal Scientific Reports, are taken from samples that were collected at platforms, ticket halls and train operator cabins from a range of popular stations, including Harry Potter's favourite, that's King's Cross, and also Paddington. Richard Harrison is with us to explain what they did. So what are these particles, Richard? And tell us more. How did you find them?
What we found is abundant nanoparticles of iron oxides within the London Underground, which we identified using sort of a magnetic monitoring technique. And these are nanoparticles generated inside the London Underground when you have the metal of the train tracks and the metal of the wheels of the Underground train rubbing past each other. So friction from that, and also in the brake systems of these trains. So if you imagine a brake disc, you have to replace that very frequently in your car, and that's because they get worn down and abraded over time. And that process of abrasion is a very powerful way of generating abundant nanoparticles of iron-rich materials. And that's what we can pick up and characterize very successfully using magnetic monitoring methods.
I was quite alarmed when I read your paper that the air quality underground is worse than the air quality overground, and London is actually ranked as one of the world's worst, or was, cities for air pollution.
Yes, it's a major problem, and it is surprising because you think going into an enclosed environment like the London Underground, you might be avoiding a lot of the air pollution that you would see overground on the streets of London. But the pollution is still there, and what's critical is that it's also a very different type of pollution. So overground, you're exposed to primarily the particulate matter that's being pumped out of the exhaust pipes of cars, whereas you have none of that in the underground system because everything's electrified. So instead, you're much more dominated by these non-exhaust emissions caused by abrasional processes between the wheels and the tracks and the brake systems and things like that.
Do you think that they have health harm implications? They're effectively rust particles if they're bits of iron oxide, aren't they?
Yeah, essentially. There's increasing work being done on this. I mean, these non-exhaust emissions are less well studied than the exhaust emissions from a health perspective, and there is sort of conflicting evidence about their long-term health impacts. But a few studies now are starting to emerge focusing on these emissions. There was one recently based on particles from the London Underground showing an increased risk of pneumococcal infection in mice, for example, exposed to those sorts of particles. And there's been some extensive work on the fact that these very, very small particles of iron oxides can enter the human body and even enter the human brain, where they've been suggested to be linked to diseases such as Alzheimer's.
Is this new pollution, or are we just churning up and recycling old pollution? Because is this a legacy of underground journeys of days gone by, and you're just detecting that every time a train goes whooshing through, it throws more of it up? Or is this genuinely generated de novo by each train that puts its brakes on?
Well, it's probably a mixture of both, but it was one of the surprising results we found was that the particles we were observing using our magnetic methods are a very oxidized form of iron. When these nanoparticles are freshly generated, they would be metallic, metal nanoparticles, but they oxidize on exposure to air, and the longer they hang around in the air, the more oxidized they will be. And so we were quite surprised to find that a lot of the particles we were seeing were this very oxidized form, suggesting that they'd been around for some time, It's hard to know exactly how long. And that these particles were, as you suggest, were being resuspended whenever a train comes through. So the particles will be being generated, but there appears to be quite a lot of legacy particles in the system as well that could be cleaned up.
So it puts a whole new spin on wear a face mask on London transport, doesn't it? Richard, thank you very much for joining us to tell us about the study. That's Richard Harrison from the University of Cambridge. He published that work this week in Scientific Reports.
On a slightly different note, quite a few of you have been in touch about the programme we made about population and overpopulation a couple of weeks ago. People seem to find it very thought-provoking, and if you'd like to explore that topic a bit more, our colleagues at the Wolf Institute in Cambridge have made a special Naked Reflections episode, 8 Billion and Counting is its title, that looks into the ethical, religious and moral side of this in more detail. You can hear it at nakedscientists.com/reflections. And sadly, that's all we have time for. Next time, we're venturing out to sea with a special look at the science of oceanography, starting with a special tour of the flagship research vessel, the David Attenborough. The Naked Scientists comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm James Titko, thanks for listening, and until next time, goodbye.